Thank you. Yeah, thank you for the introduction. So I'm Wenting from CMU, and if you look on the agenda, I think I have a much longer title, but I realized that I have the longest title, I think, out of everybody here, so I shortened it a little bit for the talk. But so basically today I'm going to be talking about the practice of MPC, and specifically I'm going to be talking about building secure collaborative systems using MPC. Oops. Okay. And I think that, I started out in working more system security, and I really became interested in secure multi-party computation because I saw that there are actually a lot of interesting workloads and use cases in industry that can be enabled by MPC, but are not able today because of, there's still a gap between theory and practice of MPC. So basically there's a need in many industry use cases for collaborative computation because you can use advanced analytics and machine learning techniques to extract a tremendous amount of value out of their collected data. But a lot of applications today that need data reside across multiple organizations, and unfortunately, due to various things like privacy concerns and regulatory constraints, these data are actually locked out. So here I'm going to, we've already seen a lot of different use cases, but here I'm going to also present another 2 use cases. So the first one is actually one of the very first real world MPC use case that I encountered, which was anti-money laundering. So we actually talked to several Canadian banks who were interested in using something like MPC to detect money laundering activities, because what's happening today is that there are, criminals, right, that launder money from bank to bank, and they try to conceal their illegal activities exactly by doing so, right? And because none of the banks, right, the banks only have their own data, they don't have access to other banks' customer transaction data, then it becomes very difficult for them to actually catch these illegal activities. And unfortunately, right, the government comes in and says, oh, well, you're not catching these illegal activities, so these banks get fined millions of dollars every year because of that. So they're really, desperate, and they really wanted to actually do some kind of collaborative computation together, either analytics or machine learning, right, over their joint data set, but they're also in competition with each other, right? And not to say, not to even consider the regulatory constraints, right? The fact that the customer transaction data is all very private, they don't even want to share data just because they're competing with each other, right? And that's customer transaction data is very valuable data. So this is something that can be enabled indeed by something like secure multi-party computation. And the second use case, I'll just very briefly go over this because we've already seen, right, multiple, Divya and Neha do a great job kind of going over this use case. So basically, right, we have this ML as an inference, ML as a service use case where you have a service provider that has a model, right, and you have a user who has some private data, and they want to do inference, join inference together so that the user can get the prediction result at the end. But unfortunately, neither party wants to reveal, either their private data or their private model, right, to the other party. And of course, we saw that, in the case of ChatGPT, unfortunately, it was actually temporarily banned in Italy due to privacy concerns. So clearly, right, there are, right, I've shown 2 use cases. We have seen many more use cases from both yesterday and today. And, MPC is something that can really enable a lot of workloads, right? A lot of new applications, exciting applications, industry. But I think that there's still a gap, right, between the theory and practice of MPC, right? In particular, right, we have seen a lot of, nice cryptographic advancements, but then kind of putting that into practice and putting that in the real application, there's still a lot of challenges. And I argue that, you can solve, try to address or try to solve some of these challenges via a co-design of computer systems techniques and also cryptographic techniques. And in particular, right, I believe that cryptography, right, using cryptography, of course, you can use cryptography in the right way, right, to build better systems, and also use systems, right, techniques to actually accelerate and democratize cryptography, right, and in particular MPC, to make it more usable and more performant. So indeed, my research group, right, we have done some different works on both sides, right, both crypto for systems as well as systems for crypto. And today I'm actually going to be just quickly going over two of these works. So one is Vault, which is a privacy-preserving inference system for transformers, which was presented at Oakland a couple of weeks ago, and there's also concurrent work with Sigma. And then after that, I'm going to be talking about Sylph, which is a framework for automatically generating MPC protocols. It's a compiler framework for doing so, and was published at Oakland last year. Okay, so one is crypto for systems, the other one is systems for crypto. Okay, so let's get started. So for both, this is a joint work with my students, Qi and Jinhao from CMU. Jinhao has since moved on to UC Berkeley. We miss him. But this is also a joint work with Thomas and his student, Helen. Okay, so, right, we've already seen this setup, so I'll go over this very quickly again, right? So basically, we're looking at the secure privacy-preserving inference setting. We have the server, which holds the model M, and we have the client who holds their private input X. And the client server in the setting are assumed to be semi-honest, where the client, the private input is X and the confidential model is M. And then we want to run a custom fast, hopefully, right, 2PC protocol, so that the client can get the prediction result, M of X, at the end to do something useful, but then we don't want to reveal M to the client or X to the server or any of the intermediate outputs, right, to any of those two parties. And just to kind of compare with the setting that the previous work, Sigma, right, looked at, we are looking not in the 2PC with pre-processing models, so we don't have another third-party dealer who can generate some, nice randomness, right, at the beginning. So we're just looking, so we're only looking at 2PC with just two parties, the client and the server. Okay, so in this setting, right, there has been a lot of work, of course, done on convolutional neural networks to try to improve the inference, right, make inference fast in that setting. For that application. But transformers are much more challenging than CNN inference because it has a ton of, more higher depth linear algebra computation compared to CNNs, in particular, not only plain text, ciphertext, matrix multiplication, but also ciphertext, matrix multiplication, and also just really non-crypto friendly the nonlinear functions, right? That we also saw in the previous talk. So it's bad news for us. So the prior work, right, in this 2PC without pre-processing model, the prior state of the art was called IRON, which tried to tackle this problem, right? Tried to tackle the transformers inference problem by building what's called a hybrid protocol to compute this end-to-end inference, right? Because we have usually, even for similar to CNNs, right? Even though transformers are more challenging, but they also kind of follow this pattern of, you have some linear layers, right? Where you're doing a bunch of matrix multiplication, linear algebra, and then you follow by some nonlinear functions, which again, right, are much harder in transformers, but still, after that, then they go back to linear and then nonlinear. So it still follows kind of this nice pattern. So IRON also uses, builds a custom, right, specialized hybrid 2PC protocol that uses both homomorphic encryption as well as a secret sharing based 2PC. In particular, they're using homomorphic encryption, which is very, linear function friendly, right, to compute the linear layers. And then, for the nonlinear layers, they're using secret sharing, right, to tackle that problem. But the problem, the drawback, right, of IRON is that even though they are trying to kind of pick the right primitives, right, to crypto primitives for the appropriate part of the, end-to-end inference workload, it still requires a huge amount of communication. In particular, in the linear layers, right, they're using homomorphic encryption, which is quite communication efficient already. But then the problem is that the way they are kind of using homomorphic encryption results in ciphertext that's very sparsely packed. So that, introduces higher communication overhead. And also their nonlinear functions that are implemented in secret sharing based 2PC are also not very crypto friendly. So as a result, what we have is something like this, right, where IRON actually consumes over 280 gigabytes of communication for one inference on BERT base, which is a transformers kind of medium-size-ish, right, transformer model, and then that actually resulted 3.5 hours for single inference in the wide area network setting. And so in both, right, we actually improve upon iron's techniques, and we have developed our own novel techniques to really reduce the communication in both the linear layers as well as the nonlinear layers, especially for the linear layers. I guess so. For the linear layers, we have almost 1700x communication efficiency over iron, and also in nonlinear, we have about 10x communication efficiency. But we do add a little bit more compute cost because we're using more homomorphic encryption, right, to reduce the communication costs, and also because nonlinear layers, they are much more communication intensive. Our overall runtime is about 10x improvement over iron. Okay, so let's see how we are able to improve the state of the art, the previous state of the art, right? And before I go into kind of the detailed techniques, let me just quickly show you the end-to-end workflow of BERT, of Bolt, right? I guess, which is doing secure inference for BERT. So the client starts with some kind of text, right? Which is, first of all, tokenized on the client and transformed into a matrix. X, which is then encrypted in homomorphic encryption and then sent over to the server, right? And as I mentioned before, we are similar to iron. We are doing we're also doing a hybrid MPC 2PC protocol. So we're kind of mixing both homomorphic encryption as well as kind of more communication, secret sharing based 2PC. So where the blue blocks are, the functions done in homomorphic encryption, and then the red blocks are the functions done in 2PC, which requires communication. So we're kind of mixing that. As you can see, BERT is pretty complicated, right, with all these different layers. And what's worse is that part is actually repeated 12 times. Yikes. But you run over all these complicated functionalities, and then at the end, the result is encrypted and given back to the client, who can decrypt the result and then get the final answer, right? Okay, so that's the general workflow. So in terms of techniques, we do have new novel techniques to improve the communication cost of both the linear layers as well as the nonlinear layers in BERT. And we also have some machine learning specific optimizations that we can apply, which is kind of, doing this as a co-design of machine learning and cryptography. And I'm going to kind of go over a few points from overall, but I'm not going to cover everything in all of our techniques for these PC on paper. So let me start with the linear layers. For linear layers, I'm going to, so linear layers, the challenge in transformers is that not only do you have plain text, ciphertext, matrix multiplication, which is basically, you have some kind of encrypted value, right? Could be the input from the client and then given to the server, and the server has the model weights in plain text, and therefore you can do a matrix plain text ciphertext matrix multiplication, or maybe in the later layers, the intermediate results are encrypted and then given to the server. Again, the server has the plain text weights, right? So you can do plain text ciphertext matrix multiplication. But the challenge is that it not only has that, but also not only has plain text ciphertext, but it also has ciphertext. But today, so we actually devise novel techniques to improve both the plain text ciphertext matrix multiply as well as a ciphertext matrix multiplication. But due to time constraint, I'm going to focus mainly on the plain text ciphertext part of the techniques. Okay, so as I mentioned earlier, so for the linear layers, right, and especially right for this specific plain text ciphertext matrix multiplication that we want to tackle, we're using homomorphic encryption for that part, and specifically we're using BFE, which is a homomorphic encryption, very popular homomorphic encryption scheme that is based on the ring LWE. And so what BFE does is that BFE can actually encode not only a single value into its ciphertext, but actually encode a vector of values, right? A vector of, essentially, you can think of it as a vector of integers into a single polynomial, and then that polynomial is encrypted, right? So it has a really nice property because it can pack multiple values into a single ciphertext, so it can amortize kind of the cost of ciphertext homomorphic operations over multiple plaintext values. So, so indeed, it supports these nice assembly applications. It supports additions as well as multiplications and rotations. And both additions and multiplications are, allow you to do element-wise addition and element-wise multiplication over vectors of plaintext, right? And the main performance overhead of BFE comes from the fact that multiplication, so additions are super easy. You basically add, right, ciphertext together, but multiplication and rotations are much more expensive because it requires kind of ciphertext maintenance techniques after you do these operations, called key switching, in order to make sure that the that you are kind of dealing with the noise and kind of readjusting the ciphertext into the right form after those operations. So therefore, additions are good, but the multiplications and rotations are slow, right? So we really want to optimize our protocol to reduce the number of multiplications and rotations used. Okay. So let's take a look at how iron, right, the prior state of the art, works in the plaintext ciphertext matrix multiplication setting. So iron actually does something super interesting. So the way that they're encoding these different plaintext values, right, these vector values into a single BFE ciphertext, is that they're actually using something called coefficient space encoding, where, I mean, that's basically what it does, right? They're kind of encoding the plaintext values in the coefficients of the polynomial. And the nice idea, right, the nice idea they had here is that if you carefully organize values in the coefficients, right, of these two polynomials, then you can actually get the inner product result by just multiplying polynomials together without any rotations. So what's happening is basically this. Here we're showing that you can compute the inner product between the first row of x and the first column y by simply multiplying these two encoded polynomials together, right? And then the end result, you can see that you get the kind of one of the dot product results, right? Number 17 in the ciphertext polynomial. So iron computes inner products of other rows and columns in a pretty similar way, and then at the end, by extracting certain coefficients in these resulting polynomials, right, then iron can actually get the correct multiplication result of z. But the drawback of this approach, right, so you kind of save some rotations, but there are actually a lot of useless polynomial coefficients in the ciphertext, and which is marked in red here. And this will actually cause some significant communication overhead because your ciphertext ends up being kind of sparsely packed, right? And then these sparsely packed ciphertexts are sent back and forth, and you get extra communication overhead. So in both, right, we instead of packing the coefficient space, we're actually going back to the evaluation space, where we actually not only pack in the evaluation space, but we also pack the columns of the ciphertext matrix into this ciphertext vector. So as you can see here, right, X is the matrix that we want to encrypt. And we are packing for the first column and then followed by the second column, etc., right, into the ciphertext. And then for the plaintext matrix, which is Y, right, in this diagram, we are packing the plaintext matrix in a diagonal way, actually in a repeated diagonal way. So what we're doing here is that we're essentially viewing matrix multiplication as a linear combination of columns, right? A linear combination of the axis columns. And as it turns out, if you pack it this way, right, in a column fashion, we actually first of all get fully compact packing, right? Everything is compact, and then using cyclic rotations to rotate the ciphertext, right, on the left, which is this CTX, to swap the positions of different columns. Then we can actually multiply with this repeated diagonal packing of the plaintext matrix, and then get the resulting Z, right, encrypted ciphertext Z. And because the way we're doing this packing, the input-output ciphertexts are all compact, so all the slots within these BFE ciphertexts are fully utilized, so we don't have any waste. So that's nice, right? That's kind of the first step. But the problem with evaluation space packing is that we do end up with rotations that are that need to be applied, right? So basically what you end up doing is you keep on having to rotate the encrypted matrix on the left-hand side column-wise, right? You shift it kind of L minus 1 times if you have L columns. So we are in a better position in terms of saving communication, right, costs, but then we're kind of introducing too many rotations, right? So how can we actually improve the number of rotations that we do? Well, so our idea here is to adapt the baby step, giant step algorithm for two matrix multiplication. So this was previously used in mostly for matrix vector multiplication, where rotations are done over single elements, but then we apply this to our matrix multiplication column level packing scheme to reduce the number of rotations that we need. So I won't go into the details of baby step, giant step, or BSGS, but the basic idea is that instead of applying all L minus 1 rotations, where again, right, if L is the number of columns that you have, we can actually reuse these rotated ciphertexts by computing matrix multiplication with them to generate partially rotated results that are offset, and then summing these partially rotated results, and then applying a backwards kind of correction rotation to the those summed partially rotated results. So this diagram kind of shows you, right, a high level of what this does, but I won't have time to explain exactly what this does. But basically, because we're not doing kind of a linear number of rotations, we're doing roughly square root of the number of rotations, right? Square root in the number of columns that we have. We're actually able to reduce the number of rotations by 17 times. So from 756 rotations to only 43 rotations. Okay, so that's kind of two techniques that we use for plain text to optimize plain text ciphertext matrix multiplication. And if we compare, do a comparison between iron and bolt, we can actually see that we achieve much better in terms of we do much better in terms of number of ciphertexts that we have. We're actually fully compact. We're not wasting any slots in the ciphertext at the cost of a bit more rotations. But then because rotations and multiplications are roughly the same cost, right, in BFE, depending on kind of which framework you use, one is slightly maybe cheaper than the other, but you can see that we actually only increase the compute overhead by about 5% while achieving complete compact packing. Okay. So that is kind of, again, right, we have ciphertext matrix multiplication techniques as well, but I won't have time to go over that today. And next, I'm going to actually move on to the nonlinear layers, right? So for the nonlinear layers, we have a bunch of techniques actually for indeed also approximating the crazy nonlinear functions that the ML folks introduce to us, but I won't have time to go over that today. Instead, I'm going to highlight a kind of interesting optimization that we found called polynomial pre-processing, which is a kind of general technique that can reduce the number of multiplications you need to evaluate a polynomial. Similar to prior works, we do, we have different approximations, but in the end, what we do is some kind of polynomial approximation, right, to approximate things like, the nonlinear functions that Neha introduced, right, GLU, softmax, etc. So, but our insight here is that, right, once you have the polynomial approximation formula, right, then it's actually possible to do some pre-processing on these polynomials beforehand if the polynomial function is already publicly known, right? So basically all the coefficients are public and known ahead of time to both parties. So for example, here where I'm showing you a kind of one way to do a one way to compute a 4-degree polynomial, right, where you are, doing these multiplications. But then with Moskin's polynomial preprocessing, which is a previously known technique, if you apply it here, then you could actually reduce the 3 multiplication between shares into to just 2 multiplications between shares, right? Just through a rewriting of the polynomial that you have. And the general case is pretty interesting that to evaluate a polynomial of degree n, then we approximately need n over 2 multiplications between shares. So this is kind of a general way of reducing the amount of multiplications you need if you have, especially if you have a kind of larger degree polynomial. And it's a kind of general, this is a pre-processing technique only on the polynomial, right? It's actually should be a general technique that might be of interest in other, for other cryptographic primitives as well. Okay, so that is it for the nonlinear layers. Finally, I'm just going to quickly go over our machine learning-based optimization, right, which is a co-design of machine learning and cryptography to further improve our performance. And really, the insight here is pretty simple, right? Actually, we just make the observation that intuitively not all tokens in a sentence actually contribute equally to the prediction. And therefore, what we need to do is compute importance scores for these tokens and only keep a portion of the tokens that are kind of more important, right, for the inference. So basically what we can do is we can actually filter out some tokens at the very beginning and to reduce the overall number of tokens that are fed into the transformer inference later on. And then, right, I won't go over the details of how we do this. Please see our paper for the techniques, but basically we're able to reduce the cost by more than 2x using this oblivious word eliminations technique. Okay, now I'm going to present a quick evaluation of both. So basically, this slide summary, right? Accuracy is pretty good. Accuracy matches in playtest models and are comparable to iron. And then in terms of the communication, the overall communication cost, we can reduce the communication cost by nearly 11x compared to iron. So here I'm showing iron on the left side and then bolt on the right side. And then the y-axis is in communication gigabytes. And finally, for the end-to-end performance in terms of runtime, we are able to outperform iron by 5.2x to 9.5x, depending on how fast the network is. So we experiment in both the wide area network as well as the local area network. Okay, so that is it for Bolt. So Bolt is a secure, privacy-preserving transformers inference system. And, we saw Sigma earlier. We just learned about Bolt. We have learned about, maybe in previous year, I don't know, there's a whole bunch of different 2PC inference papers out there. I've also worked on some of the previous ones as well. There's really a ton of them right out there, which, could be available to be deployed in industry, right? But then when you actually think about what happens in real deployment, so maybe let's just go back to the anti-money laundering example that use case I showed before, right? What does our programmer, right? So we have some, one of the banks, right, has some programmers and they're put into charge into investigating MPC. And initially they're super excited, right, about this, right? MPC looks like a very cool technique. But then what they end up finding is that, first of all, there's a whole bunch, right? They find a whole bunch of relevant work on the previous slide. And then more every year published in Oakland and using security. And then they become sad because they kind of have no limited to no expertise in cryptography. They don't really understand, a lot of these programmers, they don't really understand anything about the intricacies of cryptography, right? So, on the one hand, they have some choices in terms of, they could try to find one of these, right? Aforementioned hand-tool protocols and hope that it will fit their application by somebody is interested in developing a hand-tool protocol, right, for a particular analytics or machine learning workload. And, maybe if it's their agenda for now, maybe later they want to change it. The protocol, the application workload has changed, but the protocol needs to also be changed, right? But the programmer has no expertise to do this. So, these hand-tool protocols, the drawbacks of them is that they're very difficult to generalize. So maybe our programmer turns to these more generic platforms, right, that can support general 2PC, right? You can kind of program in some, maybe some gates, using some gates, and then you can kind of write anything technically, right, in a lot of these frameworks. But the problem is that, well, first of all, it's a bit unclear which frameworks you use even, right? There are a ton of those frameworks out there. And also, it really lacks the optimizations, right, that I discussed earlier. My student kind of spent a while, right, thinking about those techniques, but and those are the techniques that can really improve the performance, right, of these two PC protocols. But our programmer here has wide expertise, so they're kind of stuck on what to do. So ideally, we want to kind of try to converge, right, the two directions a little bit. So the question is, can we actually build a system to automatically generate some kind of optimized 2PC or MPC execution for any custom workload, right? Can we actually generalize some of the insights that I discussed before and automate them, right? So put them into a compiler so that the compiler can automatically do those optimizations for you. And of course, that's generally a pretty hard problem, right? We're kind of taking it step by step, but here I'm going to focus on one of the common optimizations that I kind of presented in bold, and also Iron uses this technique, right? Which is building hybrid protocols, right? Hybrid MPC protocols that use a variety of different MPC primitives, such as homomorphic encryption, such as secret sharing-based 2PC, such as garbled circuits, right? They're all kind of good for some scenarios, some kind of computation, but not good for all kinds of computation that you have, right? So what ideally we would want is this kind of system, right? Where you have some kind of MPC compiler where the user just writes in high-level program like C, or have a level language like C, right, or Python, and then the compiler itself can perhaps, right, do a pass over the program and then automatically figure out which part of the program should be put into which primitive, right? Which part of the program should use arithmetic secret sharing, which part should be using garbled circuits, right? And then also put the secure conversions in between them, because if you want to mix these protocols together, you need to convert between them as well. So something like this would be ideal. And we kind of call this the hybrid protocol assignment problem. So the goal of this is to find the most performant combination of MPC primitives given a particular high-level computation, right? Again, written in C or written in Python, something like that. And to do this, right, the compiler needs to know some basic information, right, such as the cost, right, the cost of each operation for each primitive. So, for example, the cost of some kind of multiplication, right, in garbled circuits versus in secret sharing versus in homomorphic encryption. And also the cost of conversion between the pairs of primitives, right? If you were to convert from HE to secret sharing, or secret sharing to garbled circuits, right? What is the cost of doing that? And then with this information in mind, for a given program, the hybrid protocol assignment problem is to simply find the set of assignments, right, such that it actually minimizes the total cost of the protocol, right? So there are kind of many different potential 2PC protocols here, but you want to find the least costly. So there are some previous works in this area, lots of interesting works in this area. So here I'm going to highlight two prior works. So one approach was proposed by a work called HiCC, which uses coarse-grained heuristics to decompose the program into larger building blocks and also assign each block a single primitive, right? So it's kind of divides the program into kind of larger blocks and assign a single primitive to each block. There's also another interesting prior work called OPA, so optimal protocol assignment. Here they're using an interesting technique where they actually start with integer linear programming. So they actually formulate the problem into an integer linear programming problem, and then they try to actually relax the ILP formulation into a linear program formulation, where the nice thing about this is that it supports fine-grained assignments. But then in this process of LP relaxation, the constraint that they had to put on the problem was that they can only mix two primitives at a time, right? So they do not support more than two primitives, and also, as we'll see later on in the evaluation, even this relaxed LP formulation actually does not scale to such a large number of constraints either. To try to address these gaps, my collaborators at CMU as well as at Stanford, we built a system called SILP, which is a framework for scalable and accurate generation of these hybrid MPC protocols. right? And because I was also collaborating with some compilers folks and who are very used to using ILP solvers and SAS solvers, right? They're excited to use them. So we initially were just like, okay, well, why don't we just formulate this as an ILP problem and just throw it at the solver, right? And see how well it does. Well, unfortunately, it doesn't do very well, so it scales very poorly as you increase the number of constraints. So basically, the x-axis shows the number of times in the computation as we scaled up a benchmark, and then the y-axis shows the solving time in minutes. And around kind of 100,000 constraints, you are already reaching solving times of 3 hours. So this is kind of scaling exponentially, which is very unacceptable for our high. So we're like, okay, well, it's not such an easy problem. Well, as expected, right? So our next goal was to, answer this question, right? Can we actually find a way to efficiently and scalably generate these optimized hybrid MPC protocols? Still using ILP, but hopefully introduce some techniques to scale this process. Okay, so the Soph, right, is this new compiler that is able to accomplish these challenges. And we kind of have multiple contributions, but at the kind of high level, very high level, right? We're able to what we're able to achieve is we're able to efficiently scale ILP for hybrid protocol assignment to achieve fast compile times and also good protocol assignments at the end. So we're able to support multiple MPC primitives, so we don't have this restriction that you can only handle 2 primitives, right, in the resulting protocol. We do that by kind of using a new ILP formulation to generate optimized protocols. And our results are that we are actually up to 30,000 x faster for compile times compared to prior works. And we are also up to 3.6x faster in terms of the generated protocol execution times. Okay, so this is the kind of the end-to-end workflow, but again, I don't have too much time to present off the techniques, so instead I'm going to just focus on one of the techniques. So we do have new ILP formulations that are different from OPA's formulation that make it easier to kind of express in ILP. And then we also have graph partitioning and mutations technique to scale ILP. And also modular optimization to also scale ILP. But I'll only have time to talk about, I'll only be focusing on graph partition mutations today. Okay, so how can we scale ILP, right? So ILP, the fundamental problem that we faced earlier was that there was way too many constraints, right, being given to an ILP solver. Okay, so one of the approaches to scaling ILP might just be to, well, let's just maybe reduce the number of constraints, right, that are being passed to the ILP solver by doing something like graph partitioning, right? So what we have here is that, just again, right, a very initial approach for doing this. The initial approach is very simple. We're simply going to graph partition the kind of the program DAG that we have into multiple partitions. Here we're just using some existing graph partitioning algorithms, which are actually pretty fast for the benchmarks that we looked at, and then we and then by doing graph partitioning, we're able to generate these partitions of the program, right? And one of the nice things of these graph partitioning techniques, these algorithms, is that they actually also basically their goals kind of align with our goals as well. So basically, the graph partitioning algorithm produce partitions that are roughly the same size, so that we are kind of not we don't have an extreme imbalance, right, in terms of number of constraints that we're solving per partition. And they also try to minimize the number of edges across the partitions. Which is also what we want to do, right? We want to kind of solve as much as possible, right, in local partition. So our initial idea was to simply, well, let's just do this, right? Let's just partition, let's just throw this, right, again to the solver now with a lot fewer constraints and see what we get, right? And the problem is that, well, this is like a simple way, right? A fast way to scale this. But if you just do this and then you repeat this step, right? This local partitioning, local partition optimization step for other local partitions, and then you rejoin each local assignment into global assignment at the end, then what you get is sometimes potentially, right, a very bad assignment because again, right, we're not solving the global optimization problem, so it's possible that we're getting not a very good assignment. So this might lead to a suboptimal solution because local assignments don't account for cross-partition edges and the potential conversion costs, right, that are applied to these edges. Right, we're already using graph partitioning to try to reduce the number of edges across, but there are still, graphs where you must have some edges, right, that cross, or, maybe even a fair amount of edges that cross from one partition to another. So this is just kind of showing this problem concretely. You can see that the local partition assigned to the last node, right, on the left is yellow, but the optimal assignment should have been blue, right, on the right side. So now we actually can incur a performance penalty if converting from yellow to red, right? That's the kind of the cross partition edge, right? If that conversion is more costly than converting from blue to red, right? And of course, we encounter this problem because we're only solving the optimization problem within a single partition without looking at anything, right, outside of the partition. To solve this accuracy problem, we introduced this heuristic, right? So this is this heuristic is this idea of mutations. So in mutations, what happens is that we actually take right, we again use graph partitioning to partition the graph, right, the DAG into multiple partitions. But then for each partition, we actually introduce some different variants, right, of the partition such that we basically expand the partitions a little bit so that we can take into account the close by neighboring nodes as well. And we're actually able to kind of expand it different levels, and then with these new partitions that we generated, we can actually again solve the local IOP problem, right, on these newly generated partitions. But now with some influence, right, from the neighboring nodes, so that we're not only always just optimizing locally without looking at anything else. And then after running this mutations optimization, mutations plus, I guess, ILP local solving, we're left with multiple new mutation assignments, right, for each local partition. And the mutations might result in slightly different assignment, right? So now, right, because we now have kind of different assignments, right, for each set of nodes that we look at, lastly, what we do is we'll combine these local mutations into a single global assignment at the end. And the goal of this combination step is to basically pick the best mutation such that it minimizes the overall cost, right, of the final protocol. And what we do is we basically run a very similar ILP construction to find the best combination mutations for a global assignment. And at this point, we basically have a global solution that should have high quality assignments and good performance. So again, I just want to emphasize that this is a heuristic, right, for scaling ILP. So if you want to find the most global optimal, you probably would have to run the entire ILP. But we do have some micro benchmarks in our paper which thoroughly study how our heuristics compare to the global ILP solution. So I won't have time to go into that, but instead I will compare with some of the baselines that I mentioned before, in particular HiCC and OPA. And we actually compare to both of these baselines in terms of compile times as well as protocol execution times, right? Those are kind of the two important metrics that we're looking at. Okay, so let's take a look at the results. So this graph shows the compile time that Sylph, has compared to HiCC, which is one of the one of the baselines that we compare to, and as you can see, for some of the there's kind of varying different performance gains that we have. So for some benchmarks, we can see that the compile time for HiCC can grow to around 2.5 hours, whereas Sylph compiles all programs under 2 minutes. And the performance gains in Sylph are due to our fast optimization passes and also scalable approach to protocol assignment. So here we tried to run HiCC, but for mini-ON, but then HiCC was unable to actually find a protocol assignment using their approach because in their code they were doing an exhaustive search. And I just want to mention that for GCD, we are 30,000x faster, but that's because of the data minimization step, circuit minimization step rather, in high CC, which took a long time. But then if you remove that, then we're about 65x faster in terms of compilation time. Okay, now let's compare with to the compilation time of OPA, right, which is the optimal protocol assignment approach, which uses the relaxed linear programming, right? So the idea right there is that LP should be easier to solve than ILP, so perhaps you can get some good performance there. But what we found was that even for LP, right, solving it is still pretty intensive for operation. And you can see that if we scale up the benchmark, right, to larger sizes, then the OPA solving time greatly dominates, whereas we are able to be very fast because of our scaling approaches. And then in terms of end-to-end compilation, time for OPA on different benchmarks, here's the result. I don't have too much time, so I'm gonna just quickly flash that, right? Let's skip. Okay, so let's take a look at protocol execution time. So compared to high CC, we're able to output from high CC in protocol execution time. We are able to find better protocol assignments compared to high CC. So for example, in the match benchmark, high CC set the assignments to use only gobble circuits, whereas SILF use a combination of arithmetic, secret sharing, and gobble circuits. And so our hybrid protocol, in this particular case, was able to lead to assignment that was 3.6x faster in execution time. When compared to OPA, we see that SILF matches the performance of OPA on 8 out of 9 benchmarks, and that's because the benchmarks, they actually use only 2 primitives to reach optimality. So the LP construction actually was optimal in that case, right? But in one particular case, I guess we were able to, we realized that we actually require all 3 primitives in order to generate optimal assignment at the end. So we were able to be a bit faster. But also, just to kind of remind you of the compilation time, we're also much faster, right, than OPA in terms of compilation time. Okay, so looking ahead, right, this is the last slide. So looking ahead, I'm super excited about the direction of co-designing between cryptography and systems. I really think that such an approach can bridge the gap between theory and practice. So on the crypto first system side, right, you can use crypto and with the application in mind, you can actually design very significantly faster, better protocols that are secure, functional, efficient. And then on the system for crypto side, I showed kind of one example where you can use system techniques to improve performance, improve usability, and accelerate adoption, right, of crypto MPC for the masses. And finally, one kind of interesting direction that I've been thinking about, but I'd love to talk to the cryptographers here, is, can we actually design better crypto primitives from scratch with systems constraints in mind? Right, so for example, I've been working on accelerator, a custom hardware accelerator for fully homomorphic encryption, which is very exciting. I love FHE. It's a super cool techniques. But then what I found was that we're always kind of behind the crypto, right? We're given this crypto and then say, hey, let's accelerate it. But then I wish that crypto perhaps could be designed with some of these systems constraints in mind. For example, function units are pretty cheap, right, on these custom accelerators, whereas memory bandwidth and also network bandwidth is pretty difficult to come by, right? And at some point, for the hardware accelerator case, right, they're only you can only build so big of a chip, right, before you kind of becomes feasible to manufacture. So that you need to, for larger workloads and for even larger, in that case, FHE parameters, you might have to scale out to multiple chips. But then that means you now need to, communicate over the network between the chips, right? And then, honestly, some of these FHE protocols or FHE schemes are not very amenable to that. So this is kind of a direction that would be very excited to explore with, together joining with cryptographers too. So please come talk to me if this is what you're interested in as well. And that's it. And I will thank you very much for the second to last talk today, coming to the second to the last talk today, and I will be happy to answer your questions.
Great.